Okay, so we are now recorded. Okay. So our topic for today is fiber optic cables, pricing, installation requirements. Okay, when you join. Wala. Okay. So lagyan ko lang ng week to. Okay. So, lesson outline, fiber optic cables, how they work, fundamentals of fiber optic cabling, and tingnan natin kung maano natin itong dalawa. Optical fiber quick connectors, saka yung how to install with a fusion splicer. Okay po. So, I'll make our topic short. Ano po? So, explain ko lang ng mabilisan. Open ko muna yung yung marker ko. So, yung submit. And tapos send ko na yung isa. Sa physical signs. Para pwede ka na-close to. Okay. So, fiber optic cables, how they work. So, ito po. So, video siya. So, play ko yung video and then share ko sa inyo. So, open ko yung YouTube. Okay. And then, ito. Copy ko lang. Okay. For a while, medyo nagalat na ng konti. Okay. Fiber optic. How they work. Kita yung screen ko ha. Tapos yung audio ko malinaw naman.
Hindi pa nga ako nakapagtulong. Paalala mo nga mamaya po ulit.
Hello. ICT nakikita po ba yung screen? Kita
Opo.
naman.
Yes, po.
Okay. So, pause ko muna. Okay. Tapos, copy ko yung link. Sige, play ko rin. So, suma. Yung sa ABM. Paste ko na lang dito. Then, share ko sa inyo. Lagyan ko ng caption to. Yan ito rin. Then share.
Ayos na, sabi.
Mawawala ko. Ganun sa laptop niya eh. Kahit tingnan ko pa.
I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand. And of course, a laser pointer. Now, keep your eye on this plug when I turn off the lights. That's wonderful. the light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass, and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto a drum. One of the greatest engineering achievements was the first ocean-spanning fiber optic cable. Called TAT-8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitmouth, England, and Ponmarsh, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire. They embedded this in an elastomer to cushion the fibers, surrounded it with steel strands, and then sealed it inside a copper cylinder to protect it from water. The final cable was less than 1 inch in diameter, yet it could handle some 40,000 simultaneous phone calls. The essence of how they send information through a fiber optic cable is very simple. I could have a prearranged signal with someone at the other end. Perhaps we'll use Morse code, and I just block the laser so that the person at that end sees flashes that communicate a message. To transmit an analog signal like voice from a phone call along the cable, engineers use pulse code modulation. We take an analog signal and cut it up into sections and then approximate the wave's loudness or amplitude as best we can. We want to make this a digital signal, which means discrete values of loudness and not just any value. For example, I'll use 4 bits, which means I have 16 possible values for the loudness. So the first 4 sections of the signal could be approximated by about 10, 12, 14, and 15. We then take each section and convert its amplitude to a series of 1s and 0s. The first bar of value 10, when encoded, becomes 1, 0, 1, 0. We can do this for each section of the curve. Now, instead of looking at the green waveform or even the blue bars, we can think of the signal as a series of 1s and 0s organized by time. And it is that sequence that we send through a fiber optic cable, a flash for a 1 and nothing for a 0. Of course, the exact method of encoding is known at the receiving end, so it is a trivial matter to decipher the message. Now, you may be wondering how a laser pulse can travel nearly 4,000 miles across the ocean. It doesn't without some help because the light will escape from the sides of the fibers. Look back at our propylene stream. Here's how the light attenuates as it travels. You can see here a narrow beam in the bucket that broadens a bit when it enters the stream, and then after the first bounce, the beam leaves even broader than it entered. That's because the interface with the air is uneven, and the rays that make up the beam strike at slightly different angles. When that beam makes its second reflection, those individual rays diverge even more, until by the time it reaches the third bounce, many of the rays are no longer at the critical angle and can exit from the sides of the stream. Here it happens in a few inches, but in a cable like TAT-8, the signal travels a stunning 50 kilometers before it needs to be amplified. Absolutely amazing. I'm Bill Hemmick, the Engineer Guy.
Excuse me po. Napanood yung video, class? Hello? Hello po. Napanood yung video?
Yes pa.
Ay, salamat, ano. Ausa and Paraleas. Okay, yung video, it tells us about how a fiber optic connection works. Okay, paano gumagana ba yung fiber, no? Kasi, yun yung nauusong connection o internet connection here in the Philippines. Ngayon pa lang, ano, kasi dati, around 2005, DSL pa yung uso, no? At ang DSL, ang gamit pong connection is copper o yung Cat5e, no? So let us go to Google. Tingnan natin yung itsura ng Cat5e. Cat5e for the image. This one. Ayan. Ganyan po yung Cat5e, yung sa RJ45. Kita po ba, class? Hello po. Ayan. Yung Cat5e
Yes,
na
ma'am.
yan, yep. Yung Cat5e na yan, this is copper, no? Ano ba yung copper, class? Diba ang daluyan yan is kuryente. Kumbaga electricity. Tama ba ako, class? Yan, no?
Yes pa.
Yan. Ngayon, that's yung DSL connection or copper connection, no? Cable connection. We have itong fiber. Yung fiber po, dun sa video, it runs through light, ilaw. And we do know, ano ba mas mabilis? Kuryente o ilaw? Sir, parehas ng kuryente ilaw. Hindi, yung light o yung electricity. Ano mas mabilis ang traveling nun? Yung light o electricity? Ano mas mabilis? Sa tingin nyo? Anyone, ICT? Pagkano nga, kailangan ko yung mga reply nyo, kaya confirmation. Ano mas mabilis mag-travel? Yung light o electricity? Hello?
Light po.
Light, di ba? Kasi
Light po.
kung nanonood kayo ng Superman, ano, sabi, it's a bird, it's a plane. No, it's Superman. Kaya daw sabi, faster than light si Superman. Ibig sabihin, kaya kinukumpara doon sa light. Unlike kasi mabilis ang travel. Okay? So, bakit po binabanggit ko yung word na light? Kasi ang fiber optic po, nagta-travel siya hindi sa electricity. Yung data nagta-transfer sa fiber optic using what? Light, ilaw, liwanag technology. Let's go here. Ano po? Yan. Kita niyo po ba to? Kaya pinatay yung ilaw para makita niyo yung green light. Kita niyo yan? Yan yung kulay green na yan.
Yes pa.
Ayan, nagta-travel, ano. So, this is an experiment para mapakita yung paano gumagana yung fiber optic, ano. Okay, kasi may sana yan. Ito pala. So, gamit siya na laser light, tapos inan niya sa bucket of water, tapos naglagay siya ng liquid, and then inano niya yung light, tapos nakita niya yung travel light dun sa butas ng bucket of water. Nagta-travel yung light, nakapansin niyo, di nawawala yung light, ano? Amazing, ano? Hanggang sa tumapon siya sa may baba. Bakit nagta-travel ang light sa tubig, sa liquid? Because of what principle? Because of refraction and reflection. What is refraction, class? Refraction is the ability of light to travel within water or within the liquid. Yung kakayanan mag-travel. At nakapagta-travel siya because of what? Reflection. Ano na may reflection? Yung bouncing of light. Okay? Through water because of hydrogen bonding. Physical science na yun, no? Next sem nyo pa mapag-aaralan yun. Anyway, ganing yung principle dun sa fiber optic connection natin. Yung bouncing of light, the traveling of light. Remember, refraction and reflection happens almost at the same time. Naintindihan ba yun? Ang comparison ko nito ng reflection at refraction, yung kulog at kidlat, magkaparehas ba yun, class? Kulog at kidlat. Hello? Tao po?
Hindi po.
Hindi. Kala ko lang tao eh. Oo, di ba? Ano ba yung kulog? Di ba ang kulog yung Yung pagka narinig mo siya, kumukulog, natatakot yung mga bata, di ba? Yung kidlat, yung liwanag, naiintindihan. Pero nangyayari ba ng halos sabay?
Opo.
Yes, halos sabay, pero hindi talaga sabay. Bakit? Nauna kasi yung liwanag eh. Remember, light travel faster than electricity, than sounds. Ayun na. Kumbaga nakita mo na, may kidlat, nasa yung tunog, nasa yung kulog. Ito na, huwag ka na mainit. Dadating yung mamaya, tamahan ka pa. Naintindihan, class? So, ganun din sa no?
Yes,
Yung traveling of light, okay, towards liquid, mabilis siya. Okay, ganun yung sa fiber optic. And let us look at the components of fiber optic. Doon tayo sa Google uli. Ito yung Cat5e sa RJ45. Sa fiber optic naman, napakinipis niya, napaka. Ayan, ganyan. Okay? At ang component ito is glasses or steel. Bakal. Bakit? Ano ba meron sa bakal? Meron siyang metal. At pag may metal, may light, tatalbog yung light. Pag tumalbog yun, may traveling na mangyayari. Naintindihan, class? Diba? Parang yung chip na aluminum, pag natama ng sikat ng araw, nakakasilaw. Kasi tumatalbog, nagre-reflect yung light. Nagre-refract yung light. Nagets po ba, class? Hello po.
Yes po.
Opo.
Okay, dito tayo So, ito yun ito yung sa fiber optic natin to. Maliit lang dito, pero ito, dinisect yung parts. Okay, meron siyang cladding. Yung cladding po, yung parang goma sa labas. Protection para sa atin. Ito, yung fully gray na yan. This is the cladding. Protection yan para sa atin. Tayo na mahawak sa fiber optic. And then, inside is meron siyang metals. Okay, bakit kailangan ng metals or steel? Para pagka pumasok yung light sa fiber optic, magta-travel siya. Kaya nga sabi, fiber optic connection pwedeng padaning sa tubig eh. Okay? Hindi ba? Yan yun. Cat8 cable. Kung sa copper cabling, we have yung Cat5e saka yung RJ45. Sa optical fiber, we have Cat8 cable. Ito yung mga steels. Okay? 6 po yan. Ito yung sa loob. Hindi, mas better tong isa. Ito. 1, 2, 3, 4, 5, 6, 6. Tapos, within that, may steels pa rito sa loob. Yung nakita nyo marami ito. So, meron tayong 1, 2, 3 layers of steel. Pinakasentro yung isa. Tapos, may 6. Tapos, nadoble dun. Okay? Tapos, yung sa labas, ito yung cladding. Ito naman yung sa loob, yung elastomer. Ito yung optical fiber o optical steel. Tapos, ito yung kulay blue or ito, kulay green na protection or coverage o covering ng yung inside, tapos yung second layer and then third layer na steel. Okay? So yun yung sa fiber optic. Ngayon, pinaka theory or principle lang dito sa fiber optic, yung paano ang pagbabasa ng data. Ito yun Remember, yung computer natin, ang kanyang language is binary, which is 1 and 0. Yun lang naintindihan niya. So, paano mo ita-transfer yun sa fiber optic? Pagka walang liwanag, 0 yun. Okay? Pagka walang liwanag. Pagka may liwanag, ibig sabihin, 1 yun. Kumbaga, on and off, on and off. Naintindihan, class? Hello po.
Yes po.
Dito yun yung pagka may kulay green, wala 0, wala siyang ilaw. Pero pagka natapat sa may 1, napakita yun dito. Dito na nga lang, play ko na nga lang. I-play natin na. Ayan.
Ones and zeros organized by time. And it is that sequence that we send through
Pero,
a fiber
para siya nagbiblink kasi pagka 1, may ilaw.
optic cable.
Pagka 0, wala. So, ang niya, parang siya nagbiblink. Nakuha po ba yung class? Hello po. Ayan. So, yun yung working ng
Yes, ma'am.
natin, fiber optic. So, let us go now to the next topic.
Di ba ka sa ano? Sa
Okay.
Philippines? Ako.
So how does it works? So paano sending ng messages? Pag may ilaw 1, pagka wala 0. At nagta-travel yung light dahil sa refraction and reflection. And yung si fiber optic hindi po kuryente, bagkus liwanag. Okay? Ayan. So we have this one, fundamentals of fiber optic cabling. So let us play this again. Sensya na, videos tayo. Hindi ko na sinama yung OH sa topic kasi yun yung parang yung pinaka-manual natin. Ano. So YouTube ulit.
Sa akin nung college, maano na daw.
Attach ko na lang itong mga, itong video lessons natin sa classroom natin this afternoon siguro. Okay. And the title is this one.
Hindi naman. Okay naman siya. Kaya lang, oo, yun nga. Minsan na lang.
Topic ko yung ano.
Pero, makakabasa naman ako ng bahay.
Search ko.
Minsan, nag-convert siya. Pero yun, sa mag-test ko lang talaga ako nagpapacheck sa ophthalmologist.
Ito. Fundamentals of fiber optic cable. Copy ko yung link. Open ko
Pacheck
video.
ko, kasi parang mas malaki yung sa iyo. Yung sa akin din, natagal na to, pero hindi naman siya sumasakit. Parang sumasakit ang ulo ko. Ulo ko. Iba ka connect.
Hey everybody.
Sa akin naman, wala rin siya. Pero nakapansin ko, may brown yung mukha. Hindi naman, may ulit siya ng mukha.
Wait lang class ha. Hintay ko lang mag-load. Commercial pa.
Hey everybody.
Okay. Tapos share ko ulit sa inyo ha. Alright. Nervin,
Sabi.
baho mo.
Bawang bulan.
Voice mo.
May tagaturo. Collaborate. May pagka-all ka, hindi ka nagsasabi, meron ka naman ng partner.
Out.
All lang.
Shut up.
Friday, this is Kevin Wallace, double CCA and Cisco Press author, and in this video we want to talk about fiber optic cabling. To begin with, let's think about physically how fiber optic cabling works. Here's an example of a very short fiber optic jumper cable that we might plug into a piece of equipment. Notice that we have 2 strands of fiber in each of these cables. One is for receive and one is for transmit. Now, by the way, the particular type of connector we have on this jumper is called an ST, or a straight tip connector. This is an MTRJ connector, and later on in this video we'll take a look at some of the different types of connectors we might have. But first, let's think about how this really works. How do we transmit binary data, ones and zeros, over a fiber optic cable? Well, it's going to use light. We might use LEDs, commonly we use lasers. But the question is, if I shoot a laser down one of these glass strands, how does it stay in that glass strand and not just get dispersed? Well, here's the way it works. Have you ever taken a glass of water and put a straw in it, as an example? And have you noticed how that straw seems to bend in the water? The reason that we get that effect is that light actually travels at a different speed in water as compared to air. It's a little bit slower in water, and air is a little bit slower than a vacuum. But that's what we're going to do. We're going to change the index of refraction of the glass to make it bend back on itself. Here's what I mean. Let's imagine that we've got this fiber optic cable, and this is the inner core. This is where the light is actually traveling in the fiber optic cable. But surrounding that core, we have the cladding. So we've got this outer type of glass. Inside of that, we have the core where the light actually travels. And the index of refraction is very different between the outer cladding and the inner core. So much so that when, let's say we've got a laser coming in here, when the light hits the boundary between the core and the cladding, the index of refraction is so great that much like that straw appearing to bend in a glass of water, it bends the light. Well, here, the indices of refraction are so different that the light actually bends back on itself. It's going to bend back like this, and you see it keeps bouncing back and forth all the way down the fiber optic cable. However, if this diameter is too large, here's what can happen. Let's say that we've got another path of light going like this. This is called a different mode of propagation. The laser came in at a slightly different angle, and as a result, it's not bouncing as much as the original beam of laser light did. Can you imagine if we extended this for 2 or 3 kilometers? The distance being traveled by each beam of light is quite a bit different. This one's bouncing back and forth, back and forth, back and forth a whole lot, and this one's barely bouncing at all. We might have yet another mode of propagation where the light almost goes right down the middle. It's going to get there faster. Can you imagine that if we had different photons representing different binary bits, that it's possible that these bits could arrive out of order? Because one bit is going back and forth, back and forth, back and forth. Even though it went first, it might not arrive before another beam of light that's going right down the middle of the fiber optic core. What I'm describing here is something called multi-mode delay distortion. Multi-mode delay distortion occurs when we have different modes of propagation extended over a long distance, and that can result in corrupted data. Maybe the data originally was we had a 0, we had a 1, we had another 0, and we're going in this direction. Because of all the different modes of propagation, it actually might arrive out of order. It might arrive as something like 1, 0, 0. We've corrupted our data. So to prevent this from happening, there's a couple things we can do. Number one, we can limit the distance. In fact, we're going to take a look later in this video at some of the distance limitations surrounding different types of fiber optic cabling. So if we don't go too far, then this is not going to be an issue. Another way to address this issue is to simply have a smaller core. With a smaller core, there's not room for all these different modes of propagation. There's only room for light to take one path down that fiber optic cable. And as a result, we don't have to worry about this multi-mode delay distortion. You're oftentimes going to see this type of fiber optic cable referred to as multi-mode fiber, and the bottom type is referred to as single-mode fiber. Those are a couple of different types we have. Now, let's go out to some slides and take a look at some specific types of cables, connectors, and distance limitations.
Now that we understand a bit about the optics in fiber optic cables, let's talk about some of the specific connectors we might run into. One that I showed you just a few moments ago was the ST connector. Sometimes that's called straight tip or bayonet. You insert this in the connector and you might be able to see that there's a spring inside the connector. You push and twist and release, and that spring creates tension to hold the connector in place. And these are fairly common. Another type you might run into is an LC connector. And some of the terminology here might vary depending on where you're reading about it. LC, some literature will tell you, stands for lucent connector or local connector or little connector. But notice that there is a push-down plastic tab that allows you to secure and then to release one of these LC connectors. An SC connector allows you to push this connector into the receptacle, and to remove it, you just push again, and it pushes in and it unlatches. And what SC stands for, again, might vary based on the literature you're reading, but some of the literature calls it a subscriber connector, or a standard connector, or a square connector. The other type of connector that I showed you just a few moments ago was an MTRJ, and the thing that's really unique about an MTRJ is it contains both fiber optic strands, one for transmit, one for receive. It contains both in a single connector, which allows us to have a higher density of connectors. An MTRJ, it might stand for
depending on your source, media termination recommended jack, or mechanical transfer register jack. Now let's imagine, and we'll just use an ST connector for this example, but let's imagine that we have a couple of ST connectors in a fiber distribution panel where we have the ends of these ST connectors bumping up against one another, and we're trying to send a light source through one connector into the other connector. If they meet with very flat surface, hopefully we're going to have very little loss. There are fiber optic polishing kits to try to minimize this loss, but there's going to be some reflection. When the light comes in, let's say from the left-hand side, and it hits that interface between the ST connectors, hopefully almost all of the light is going to pass through and go into that other connector and onto its destination. But no matter how much we polish, there's going to be a little bit of reflection. And that reflection could come back to us. It could come back to the optical source, the laser, and actually damage that laser in some cases. So many people, instead of using this approach where we have a flat surface touching a flat surface, which is known as a UPC, an ultra physical contact, some people prefer to use an APC, which is an angled physical contact. Here, when we put these connectors together, they don't completely touch. It's not a flat surface meeting a flat surface. There's actually an 8-degree angle between these. And this is called, again, an angled physical contact. And the idea is the tiny bit of reflection that we get is not going to go straight back and damage the optical source. It's going to be dissipated in the cladding of the fiber. Now let's wrap up this video by taking a look at some of the distance limitations of different types of fiber optic cables. And we'll do this by considering some of the Ethernet standards that are popular out there. If we have twisted pair cabling and we're running fast Ethernet, we're running a 100 base TX, then on something like category 5 or higher, we're going to be able to send 100 megabits per second for 100 meters. If we're doing 1000 base T, that's a gig. We'll be able to send a gigabit per second over, again, 100 meters. Now let's go into our fiber optic cabling. If we have 1000 base LX, the 1000 tells us that we're transmitting at 1 gigabit per second, but the distance limitation is a bit different depending on whether we're using MMF, multi-mode fiber, remember the multi-mode delay distortion, or SMF, single-mode fiber. With multi-mode fiber, our distance limitation is 550 meters, but if we just have a single mode of propagation, if we're using single-mode fiber, we can go for 5 kilometers. Another Ethernet standard that uses fiber is 1000 base SX. This is a multi-mode fiber standard. It again has a throughput of 1 gigabit per second, and here the distance limitation varies based on the diameter of that core. It's really common to have 62.5 micrometers as the diameter of a core in a multi-mode fiber. That's what I was showing you a few moments ago. And if that's what we're using, the distance limitation is 220 meters, but if we have a smaller core, still multi-mode fiber, we can still have multiple modes of propagation, but not as many. Our distance limitation is going to be 50 micrometers. And hopefully that gives you a sense for how distance limitations can vary based on the type of fiber optic cable that we're using. To its destination, but no matter how much we polish, there's going to be a little bit of reflection, and that reflection could come back to us. It could come back to the
Okay, napanood ko yung video class.
Opo.
Yes pa.
Okay. So, continuation dun sa topic kanina, no? How it works. And the difference is, let's go to the video. Okay, ito. Sinasabi niya, no, here, na pagka mas makapal yung connector, may bouncing na nangyayari, no? Because of that refraction and reflection, na action, ng light. Pero kung straight, mas manipis, dire-diretso lang yung light. So there are two kinds, we have yung MMF, multi-mode function, and then we have SMF, yung straight lang, so single or straight mode function. Much better yung single or yung straight. Okay? Tapos, ito yung different types of fiber connectors. Okay? We have, I think, 6. So, pa-check na lang sa attachment ng video na ito. We have 5 or 4. Hindi ko lang klasa.
In a fiber distribution panel,
Apat lang. So, we have ST fiber connector. We have LC fiber connector. We have SC fiber connector and MTRJ fiber connector. MTRJ ito yung multi, isang limbang multi kasi dalawang yung channel. Then we have yung yung LC tapos SC tapos ST. Then aside from that, merong UPC, yung diretso, yung pinagduktong lang yung dalawa. At meron tayong aside from UPC, we have this one, yung APC, yung angled, para may konti lang yung diferensya, kumbaga may bouncing nangyayari. And we have our Ethernet standard. Okay, we have this list or chart. We have 4. Pagka 100 base TX, we have 100 Mbps, distance is 100 meters. 1000 base dash T, we have 1 gigabyte per second, and then 100 meters yung limitation. Then sa 1000 base LX, we have for multi-mode 1 gigabytes per second din, pero ang kanyang distance po ay 550 meters lang. Then dun sa 1000 base na LX, yung SMF or single mode, we have 1 gigabytes per second din, pero the distance is very long, which is 5 kilometers. And the last but not least, if we have 1000 base SX, for multi-mode, we have 1 gigabytes, and that is 220 meters lamang. Ayan.
it's 1000 base SX. This is a multi-mode fiber standard. It again has a throughput of 1 gigabit per second.
Okay, yan yung Ethernet standard. So from this video class, paki-take note yung Ethernet standards, pati yung types ng fiber connectors, kasi baka isama ko sa quiz niyo po yun. Naintindihan po, class?
Opo.
Yes pa.
Okay. So later this afternoon ko i-attach tong video na to, Okay, last but not the least, last topic.
And here,
Last
the
topic
distance
na tayo.
limitation varies based
Okay, yung paggamit ng kasi may pa-manual na pagkakabit nito, i-attach ko na lang yun. Kaso lang very tedious at delikado, kasi pag nagkamali ka, bagong gamit uli, napakamahal ng gamit sa fiber optic. Tapos, meron tayong fusion splicer. So, hanapin ko yung fusion splicer na yun. Ito yung isa, yung pa-manual. Medyo tedious to, so I do not suggest that. Pero ito yung para kung wala kang budget, you can do this. And we have this one. Ito, pagka may pera ka, kasi lang mahal ng splicer, around 30,000 o 45,000. So, very costly. Ayan. Pero, ilalagay mo lang yung fiber, tas okay na siya. Ganun kaganda yung fusion splicer. Nga lang, maganda rin yung presyo. So, play ko na lang. Okay, fusion splicer. Fusion splicer. This is Wireworks, ng Wireworks. Ilan minutes yun? 6:11. 6:11. Eto? Ito ata yun. Wireworks pa to. Oh, ito nga. Wireworks. Okay, copy ko yung link. Space ko. Okay, so share ko na po yung video sa inyo. Okay, for a while lang.
Dapat mo kasi pasok.
Get ID cam, ano yun?
Di ba baka nagdalaw ni Darwin po?
Hello po. Hello? Napanood yung video class. So yun yung mga steps ng paano gumamit ng
Yes, pa.
Fusion Splicer, no? Which is a costly equipment, ano? Around 30,000 o 45,000, ano? Fusion Splicer. Kaya siya fusion kasi yung connector na isa, yung pantake, pati yung fiber optic natin, pinag-fuse doon sa machine, ano? So, i-clip mo muna yon. So, may cleaver tayo na machine, tapos may fusion splicer. I-clip mo muna siya, pag na-clip, saka yung fuse. So, pakiano na lang yung ano may steps naman na nakalagay doon. So, siguro, rearranging kayo when it comes to our quiz. Okay? So, yun yung lesson natin for today, which is fiber optic. You have your task or assignment. Ilalagay ko lang later this afternoon. So, better check that. Magme-message na lang ako sa GC later for your assignment. Deadline is 1 week. So, kindly accomplish na lang po yun. Naintindihan po ba, class?
Opo.
Okay.
Yes, pa.
Stop ko na yung recording. So, upload ko na lang din